Right now, I mean, if you look at the most powerful artificial intelligence models on Earth, they basically live inside these concrete buildings the size of, well, shopping malls.
Oh, yeah. Massive.
Yeah, we're talking about massive, multi-trillion-dollar infrastructure projects, just packed with tens of thousands of NVIDIA GPUs.
Sucking up the electricity of entirely small cities.
Exactly. I mean, they literally demand their own dedicated nuclear cooling towers. And you have probably been told that this is the only way the future of AI works.
Right. That true intelligence requires this huge industrial-scale computing factory.
But a few days ago, a lone developer kind of shattered that entire illusion. He took one of those massive city-draining data center-grade AI brains, and he just crammed it into the consumer laptop sitting in his backpack.
Which, I mean, physically speaking, violates almost everything we traditionally understand about how computing memory actually works.
Yeah.
The hardware limitations alone should have caused the machine to just instantly crash.
Completely impossible. Yet it happened. So welcome to this deep dive. Today, you and I are looking at two highly revealing sources that really explain this disruption. First, we have a recent article from Cult of Mac that details this developer's shocking breakthrough. And second, the secret sauce behind it all.
Oh, this paper.
Yeah, it's an incredibly dense, highly technical 2023 research paper from Apple. It's titled LLM in a Flash, Efficient Large Language Model Inference with Limited Memory.
A very catchy title.
Right. But our mission today for you, the listener, is to figure out exactly how this impossible feat was accomplished. We're going to break down the brilliant engineering tricks that make it work and really explore why the ultimate AI device of the future might already be, sitting on your kitchen table. Okay, let's unpack this.
To really grasp the magnitude of the disruption here, we need to look at the sheer scale of what this developer, Dan Woods, actually achieved.
Yeah, the numbers are wild.
The math is staggering. So he ran a model called Qwen 3.5397B on a MacBook Pro with an M3 Max chip.
I want to pause on that name for a second. Qwen 3.5397B, because those numbers are the core of the whole problem here.
Right.
That 397B stands for 397 billion parameters. For anyone trying to visualize that, think of parameters as like the individual neural connections or the synapses in the AI's brain.
That is a really helpful way to picture it, actually. And a brain with 397 billion connections is absolutely massive.
That's huge.
It's what we consider a frontier model. It puts it in the exact same heavyweight class as the models powering ChatGPT or Claude.
Right.
And to store all those billions of parameters uncompressed, the model takes up 209 gigabytes of disk space.
209 gigabytes.
Yeah. And even when Woods used this intense mathematical compression to shrink it down, the file still sat at 120 gigabytes.
And here's the collision course, right?
Yeah.
He ran a 120 gigabyte brain on a laptop that only has 48 gigabytes of working memory, or RAM.
Yeah, the math doesn't work.
We have a skull that is less than half the size of the brain we're trying to stuff into it. Yeah. It simply does not fit.
It doesn't. And yet, Woods didn't just get the model to boot up without crashing, which would be impressive enough.
Right.
He actually got it generating text at a remarkably fast pace, over 5.5 tokens or words per second.
Okay, to understand how wild that 5.5 words a second actually is, we need to talk about the physical bottleneck of traditional computers.
Let's do it.
Imagine your computer's RAM, the working memory, is a small, really fast desk. You're sitting at this desk, you're actively reading books, taking notes, moving incredibly fast.
Okay.
But the flash memory, so your SSD or your hard drive where all your files are permanently saved, that is a massive dark warehouse right next door.
That analogy maps perfectly to the actual architecture.
Okay, good.
Because normally an AI model needs to sit entirely on that fast disk in the RAM to function. It needs all of its 397 billion parameters instantly accessible at like a millisecond's notice.
Right, right.
If the book you need to read is too big for the desk, it falls off, the system panics, and you get an out-of-memory error. Everything shuts down.
So the obvious, naive solution would just be to say, well, if the desk is too small, I'll just leave the encyclopedia in the warehouse. I'll just run into the warehouse and grab the specific pages I need while I'm writing. Why doesn't that work?
Because of a severe bottleneck called bandwidth. The Apple research paper lays out the data on this beautifully.
Yep.
Your flash memory, the warehouse, has massive capacity. You can easily have a terabyte of storage in there. But its bandwidth, the speed at which you can physically carry boxes out of the warehouse doors, is terrible.
Like how terrible?
It can generally only transfer data at about 1 gigabyte per second.
Which, I mean, sounds fast to me until you compare it to the desk.
Exactly. It's 2 orders of magnitude slower, to be precise.
Wow.
The DRAM, your desk, operates at around 100 gigabytes per second. It is built for lightning-fast simultaneous access.
Okay, I see the problem.
Yeah, if you attempt to constantly reload a massive AI model from the slow flash memory warehouse into the fast DRAM desk for every single word the AI generates,
It's just too slow.
the latency would be catastrophic.
You wouldn't be getting 5.5 words a second. You'd be waiting, what, several seconds just to see a single syllable pop up on your screen.
Easily.
And I'm assuming your laptop battery would probably melt from the physical effort of spinning up the SSD to run back and forth to the warehouse thousands of times a minute.
Oh, absolutely. The energy inefficiency would make it completely unusable on a battery-powered device.
So we have established the physical laws of the universe here. The desk is too small, and the door to the warehouse is just too narrow.
Correct.
Dan Woods couldn't change the hardware, obviously, so he used a playbook that Apple's own engineers quietly published back in 2023.
The LLM in a flash paper.
Yeah.
The brilliance of this research is that it stops treating the AI like a monolithic, solid object that has to be moved all at once.
Okay.
Instead, it solves the hardware problem with a really profound understanding of how large language models actually think.
How so?
The core thesis is to leave the vast majority of the model in the flash storage, the warehouse, and stream only the absolutely essential pieces into the RAM at the exact millisecond they're needed.
But wait, how could the system possibly know which pieces of a 397 billion parameter brain are essential at any given millisecond?
That brings us to a foundational concept in the paper known as sparsity.
Sparsity?
Yes. As it turns out, large language models are surprisingly sparse in their operations. When they generate a single word, they do not use their entire brain.
Really?
Yeah, the Apple researchers tested this using a model called OPT 6.7b.
Okay.
They applied a specific mathematical activation function called ReLU, which stands for rectified linear unit.
Right, I've seen that term.
When they monitored the model's feed-forward network layers, they observed 97% sparsity.
Hold on, 97%.
97%.
Are you telling me that when the AI writes a sentence, 97% of its artificial brain is completely dead weight for that specific moment?
Basically, yes.
That sounds wildly inefficient. I mean, why build a massive brain if you only use 3% of it at a time?
I know, it seems counterintuitive until you consider specialization.
Okay.
The ReLU function acts as a strict mathematical gate. If the data signal passing through a specific neuron falls below a certain threshold, the ReLU function turns the output into a literal zero.
It just shuts it off.
It deactivates the neuron entirely. And the reason this happens is that AI models learn highly specialized representations.
Give me an example.
Okay, if the AI is generating a word about quantum physics, the neurons trained on 18th century French poetry have absolutely nothing useful to add.
Right, that makes sense.
So the ReLU gate shuts them down, meaning only 3% of the neurons are actually firing and contributing to the next word.
Okay, let me make sure I'm following the logic here. If we know that 97% of the brain isn't firing, we don't need to put that 97% on our small RAM desk. We can just leave it in the warehouse.
Yeah.
But that still leaves a glaring problem for me. If we only load 3% of the model's knowledge, doesn't it lose its smartness? I mean, let's be real. If you leave 97% of my brain in a warehouse, I'm going to start forgetting facts and hallucinating.
That is the ultimate risk, yes. And it is exactly why naive streaming fails.
Okay.
If you guess wrong and leave a crucial neuron in the warehouse, the AI's reasoning completely collapses.
Right.
So to solve this, the Apple engineers built something they call a low-rank predictor.
Low-rank predictor.
Yeah, it's a tiny, highly efficient secondary AI model. It runs continuously, just slightly ahead of the main massive model.
Okay.
Its sole purpose in life is to analyze the context of the sentence and predict exactly which 3% of the neurons the main model is going to need for the next word.
Oh, I see. So going back to our analogy, we aren't just blindly running into the warehouse hoping we find the right book.
Right.
We have basically hired a psychic librarian.
A psychic librarian is a perfect way to visualize the low-rank predictor.
I love that. So instead of you having to drag the entire 209 gigabyte encyclopedia onto your tiny desk, the psychic librarian is standing in the dark warehouse. And because they're reading over your shoulder, they know exactly which 3 pages you are going to ask for next.
Yes.
They sprint to the desk and hand you only those pages exactly when you need them, leaving all the rest of the heavy books on the shelf.
Exactly. And to address your concern about the AI losing its intelligence, the paper rigorously proves the psychic librarian actually works.
Oh, they tested the accuracy.
They did. In Table 1 of the study, researchers ran zero-shot performance metrics.
Okay.
These are tests like ArcEasy, which tests basic reasoning and science facts, and HelloSwag, which tests common sense sentence completion.
Got it.
The data showed that using this tiny predictor to fetch only 3% of the model did not adversely affect the model's baseline accuracy at all.
Not at all, no.
The false negatives, so the neurons it accidentally left in the warehouse, they were mathematically so close to zero anyway that their absence did not change the final output.
That is genuinely wild. So we solved the capacity problem.
Yes.
We know what data to get from the SSD warehouse, and we know we only need a tiny fraction of it. But we still have that physical speed problem.
The latency.
Yeah. Fetching thousands of tiny random bits of data from an SSD is painfully slow.
It is severely bottlenecked by latency, you're right. Flash memory architecture hates small, random reads.
Why is that?
Because every single time you ask the SSD for a piece of data, there is a communication delay. The operating system, the hardware drivers, and the flash controller all have to talk to each other to find the address of that specific data.
That sounds exhausting.
It is. If you ask for 1,000 tiny scattered pieces of data, you pay that latency toll 1,000 times.
It's like paying a separate delivery fee for every single page the librarian brings you.
Exactly.
So how did Apple engineers speed up the physical reading process to get those 5.5 words a second?
They employed a series of hardware-aware engineering tricks, starting with something called row-column bundling.
Okay, unpack that for me.
While flash memory hates random reads, it loves large sequential reads.
Yeah.
It wants to grab a big continuous chunk of data all at once. So the engineers looked at the underlying math of the AI's brain, specifically the up projection columns and the down projection rows.
Okay, get a little mathy, but I'm with you.
They realized that due to the matrix math involved, whenever a specific neuron fires, you will always need its corresponding row and column together.
They're a package deal. You never need one without the other.
Precisely. In a traditional setup, those rows and columns might be stored in totally different parts of the flash drive.
Which means more random reading.
Right. So Apple's engineers reorganized how the data is physically written to the drive. They bundled those interdependent rows and columns together into single continuous blocks.
Right.
By doing that, they instantly doubled the chunk size of the data being read in a single trip. They pay the latency toll once instead of twice, which appeases the hardware controller and massively increases the data throughput.
Okay, so they're carrying bigger, more organized boxes out of the warehouse. Is there a way to avoid going back to the warehouse entirely for every single word?
Yes, and it relies on understanding how human language naturally works. The researchers instituted what they call a sliding window technique.
A sliding window. How does that work in practice?
Language is highly contextual.
Yeah.
If I am talking to you about a bank and I use the word river, the specific neurons in the AI related to water, nature, and geography are going to fire.
Right, because of the context.
And because of how sentences are structured, those exact same nature neurons are highly likely to keep firing for the next few words.
Yeah, that makes sense.
So instead of deleting those active neurons from the RAM disk immediately after generating a single word, the system caches them.
It just leaves them on the desk.
Exactly. It keeps the active neurons from the past few tokens, say the last 5 words, in a continuous window on the desk.
Oh, that is brilliant. It's a predictive cache based on the subject matter. Because you are likely to use them again, the psychic librarian doesn't need to bring the whole 3% from the warehouse for the next word.
Right.
They only have to load the incremental difference, just a few new neurons that weren't already sitting on the desk from the previous word.
What's fascinating here is how software is being radically bent to accommodate the physical realities of hardware.
Yeah.
And they went even further with a memory management hack involving pointer swapping.
Pointer swapping.
Normally, when you move data in and out of RAM, the computer is forced to constantly reallocate memory space. It deletes old data, searches the RAM for new empty space, and writes the new data there.
Okay.
That constant rewriting wastes a massive amount of computational time.
To use our desk analogy again, it would be like sweeping everything off your desk into the trash, wiping the desk down with a towel, and then carefully placing the new books down every single time.
It's exhausting just thinking about it.
Yeah, it's incredibly inefficient.
So Apple's fix was a beautifully geeky sleight of hand. They pre-allocate the memory space right at the start. They map out a permanent grid on the desk.
Aye.
When new neurons come in from the warehouse, they don't delete and rewrite the old ones. They simply stack the new data in the pre-allocated grid.
Oh, I see.
Then, instead of moving the heavy data around to where the computer expects it, they just swap the underlying memory pointers.
They just change the sticky notes on the folders.
Exactly.
They tell the computer, hey, the data you're looking for is over here now, without actually moving the heavy boxes of data.
That is exactly what pointer swapping does. It eliminates almost all unnecessary data movement within the RAM.
Wow.
And the results of combining all these techniques, the sparsity, the predictor, the bundling, the sliding window, and the memory hacks, they are staggering.
What were the actual results?
The 2023 paper demonstrated they could run models twice the size of the available DRAM.
Twice the size.
Yes. They achieved a 4x to 5x speedup on CPUs and up to a 20x speedup on GPUs compared to the naive brute force loading method.
So Apple proved the math. They proved the physics. But this was 2023. And it was just a dense research paper.
Right. It lived in a PDF.
Yeah, it took a developer, Dan Woods, in 2026 to actually apply this theory to a massive modern model and make it real for consumers. Let's talk about how he actually built this.
Woods was remarkably strategic in his implementation. He didn't just pick any model. He chose Qwen 3.5,
Okay.
which utilizes a MOE architecture. That stands for a mixture of experts.
Okay, what makes a mixture of experts different from a standard AI model?
Traditional models act as one giant interconnected brain, and MOE model is inherently modular. It is a collection of sub-experts, smaller, specialized neural networks tied together by a routing mechanism.
Like a team of specialists.
Exactly. When you give the AI a prompt, the router decides which specific experts to consult for that token. Woods took this highly capable Qwen model and manually tweaked it.
What did he change?
He dropped the number of active experts queried per token from 10 down to 4.
Okay, dropping from 10 experts to 4 sounds like a massive downgrade in intelligence.
It does sound like it.
Why doesn't the AI get dumber if we silence 60% of its experts?
Because of the same principle of specialization we discussed with sparsity earlier.
Oh, right.
For any specific task, whether it's writing Python code or translating French, only a few hyper-specialized experts in that network actually hold the mathematically correct answer.
Okay.
The other 6 experts are just adding computational noise and taking up memory. By dropping the irrelevant ones, he massively dropped the memory demands without losing the actual genius of the model.
Wow.
This allowed the MOE architecture to fit perfectly into Apple's optimized streaming pipeline.
Here's where it gets really interesting, though. We are talking about incredibly dense, low-level optimization here.
Very low level.
Matrix bundling, manipulating memory pointers, tweaking MOE routers. How did one guy write all this complex code? Did he spend 6 months manually typing out matrix math in C++?
He did not. And this is perhaps the most indicative part of where software development is actually heading.
Yeah.
He used an AI to build the software that runs the AI.
The Cult of Mac article calls it vibe coding, which is such a great term.
It is very 2026.
He essentially acted as a high-level director.
Yeah.
He took the dense Apple research paper, fed it into an AI coding tool called Claude Code, and basically set up an automated research loop.
Right.
He had the AI run 90 automated experiments,
Right.
and the AI itself wrote the highly optimized MLX Objective-C and Metal code.
For context for the listener, Metal is Apple's low-level graphics and compute API.
Right.
It is notoriously difficult to write by hand because it talks directly to the silicon chips.
And Woods didn't have to write it. He just managed the AI that wrote it.
Yeah.
It completely shifts the identity of a developer from someone who, memorized syntax to someone who understands system-level architecture.
Absolutely. Woods understood the theory of the Apple paper, and he just used Claude to hammer out the flawless execution.
But this raises an important question about the hardware itself. We've discussed all these brilliant software tricks, but why a MacBook Pro? I mean, why not a tricked-out Windows PC with top-of-the-line components?
That is the million-dollar question.
Yeah, if I have a massive gaming PC at home, can I just run this same Apple playbook on my machine?
Generally, no. And this is where we see the physical advantage of Apple's hardware strategy.
Sorry, explain that.
Traditional PCs use a divided architecture. Your main processor, the CPU, has its own system RAM. Your graphics card, the GPU, which is what actually processes AI math, has its own dedicated video RAM, or VRAM.
Right.
When they need to share information, they have to send it back and forth across a physical bridge on the motherboard called the PCIe bus.
Which acts as another massive bottleneck.
A severe one, yes. But so the M1, M2, M3 chips uses what is called a unified memory architecture.
Unified memory.
The CPU and the GPU are built onto the exact same chip, and they share the exact same pool of high bandwidth memory.
They're literally sitting at the exact same desk. There is no bridge to cross.
None at all. Furthermore, that unified memory sits in unusually tight coordination with the Mac's ultra-fast NVMe SSD storage. The data pathways between the flash warehouse and the DRAM desk are wider and faster than almost anything else on the consumer market.
Wow.
It is the perfect, literal, physical environment for the LLM in a flash technique.
If we connect this to the bigger picture, it is just such sweet irony.
Oh, totally.
For years, Apple has been the punchline of the AI race. They were openly mocked by Wall Street for falling behind OpenAI, Microsoft, and Google.
Right. Siri has been the butt of tech jokes for a decade.
Exactly. But this deep dive reveals something entirely different. While everyone else was rushing to build giant billion-dollar server farms, Apple might have quietly, methodically, built the ultimate personal AI hardware all along.
Yeah, they just didn't tell anyone what those chips were really capable of until the software caught up.
It's crazy.
It completely reframes their entire hardware strategy. The MacBook Pro isn't just a laptop that can sort of run AI on the side.
No.
From the unified memory to the neural engine, it was designed from the ground up to be a local AI powerhouse.
So what does this all mean? Let's do a quick recap of this incredible journey for you listening at home.
Let's do it.
By understanding the natural sparsity of how language models actually think and pairing that with psychic little predictor models that know what data is needed next, we solve the capacity problem.
And by using clever engineering tricks like bundling flash storage reads, utilizing a sliding window for context, and manipulating memory pointers to avoid rewriting data.
We solve the speed problem.
Exactly. We solve the speed problem.
And when you combine all of that software genius with the physical layout of Apple's unified memory architecture, a single developer with a consumer laptop just took on the capability of a multi-million-dollar data center rack and won.
It's incredible.
But the real victory here is what this means for you, the listener. Local AI completely changes the game.
Oh, absolutely.
First, there is absolute privacy. If a frontier model is running entirely on your laptop, your private prompts, your sensitive corporate data, your personal files, none of it ever gets sent to a cloud server.
The security implications for medical, legal, and corporate use cases are profound. You basically get the intelligence of the cloud with the security of a locked safe.
Right. Second, the speeds. When you don't have to wait for your prompt to travel through the internet to a data center in Virginia, get processed, and travel back, the response is virtually instantaneous.
Zero latency from the network.
Exactly. And third, zero subscription fees. You aren't paying 20 or 30 bucks a month for cloud access anymore.
Yeah.
The most powerful AI model in the world might soon just be a local open source app sitting on your laptop running completely for free.
It fundamentally disrupts the economic model of the current AI boom, which completely relies on renting you access to intelligence.
It really does. And it leaves us with a pretty wild thought to chew on as we wrap up today.
What's that?
Well, we started this deep dive talking about the massive tech monopolies, the Amazons, Googles, and OpenAIs spending billions to build giant AI factories.
Right.
Their entire future business model relies on them controlling the hardware, hoarding the intelligence in their data centers, and basically acting as the gatekeepers of this technology.
You're true.
But if developers can now use vibe coding to run massive open source frontier models natively on the laptops sitting on our kitchen tables, what happens to that immense power and control?
That's a huge question.
Are we witnessing the start of the decentralization of the most powerful technology in human history?
It really makes you wonder.
Because if the AI revolution doesn't actually require a shopping mall-sized data center after all, then the future might not belong to the giant tech monopolies. It might just belong to whatever is sitting right there in your backpack. Thank you for joining us.